So, welcome back to this class. We will look at how to use compressibility charts for dealing with gases which are not ideal. So, here we have a chart which shows a plot of Z, which is the compressibility factor given as PV by RT, versus what is called as the reduced pressure, which is PR. So, the reduced pressure is essentially the pressure which is there divided by the critical pressure. We will look at what is the critical pressure in a few moments. And similarly, we have this notation TR here, which is the reduced temperature, which is essentially the temperature divided by the critical temperature. So, we will see what the critical temperature is also in a few moments, but for the time being this is what we will say. PR is P by Pc, TR is T by Tc. So, if the gas was an ideal gas, we would expect the value of Z to be 1 irrespective of what the pressure or the temperature is. What we know from earlier is that when the pressure is low, then the space between the molecules is high, then the molecules do not attract themselves very highly, and we expect the gases to behave as ideal, which is essentially what we also see. So, if we go on this plot towards the left where the pressures are low, what we see is irrespective of what the temperature is. So, for here example TR is 1, TR is 1.1 and so on. As we go up this way, we have an increasing value of the temperature. So, as we go to any temperature, as long as we are very close to the left hand side of this plot, we see that the value of compressibility factor is close to 1. So, gases behave as near ideal when the pressure is very low irrespective of what the temperature is. What we also see is that if we go to high temperatures, for example, if we go to TR is equal to 2, irrespective of what the pressure is, whether we are on the left of this curve or right of this curve, we are close to this value of 1. So, if the temperatures are about twice the critical point, so we said TR is T by Tc. So, if TR is about 2 times Tc, which is this red curve, irrespective of what the pressure is, the gas behaves in a more or less ideal fashion. So, we now have some kind of a definition for an ideal gas or some kind of a definition for when a gas is ideal. So, we can either be at very low pressures or be at temperatures more than say twice the critical temperature. Then the gases behave as if they are ideal and the ideal gas laws are applicable. So, what do we do at other conditions? So, here for example, we have, let us say, this curve over here, this red curve over here. This red curve has data for all kinds of gases. For example, it has data for methane, it has data, these circles for ethylene, it has this green circles for isopentane and so on. It has the data for a lot of points, some of them are not very clearly visible, but that is all right. So, the more important thing about this plot is that if it is plotted on this scale where we have Z versus PR with TR on it, then it does not matter what the substance is, all of the substances follow the same trend, which is quite interesting. So, which means I can use this single plot to find out a relation between properties of various substances, whether it is carbon dioxide or water or nitrogen or methane. I do not have to worry about what it is. As long as I have this plot, I can compare all of these substances and find out properties, relations between them. So, now for example, if I was to look at say some point over here, let us say I am interested in finding out properties at a reduced pressure of 2. So, the critical pressure and critical temperature are fixed for a specific gas. So, for example, we will look at the data for water in a few minutes. For water, this is close to about 220 bar and about 374 degrees centigrade. We look at the actual values. So, if I was at a pressure of say 1 TR, so which means if, or let us say 1.1 TR, and if I was at a pressure of say 2 PR, then that would give me this point over here. So, the intersection of TR equal to 1.1 and PR is equal to 2. If I wanted to know now what the volume is over here, what I can do is find out the value of Z, which is about 0.4. Assuming that the gas is ideal, I would get PV is equal to RT which would give me what the volume would be if the gas was ideal. What this tells me is that this is not going to be my real volume. My real volume is going to be only 0.4 times whatever it would be otherwise. So, now what I have is that V for the real gas, I have V is Z times RT by P. This is if it was ideal, and for the real gas, I have the Z times RT by P. So, I would find out Z from this chart, say it is 0.4 for this particular point, and then have R, assuming it is an ideal gas. I have T, which I know, and I have P, and I can find out what now the actual volume is. This would be the ideal volume, and this is the actual volume. Similarly, for example, at some other condition, let us say I wanted to know what is the volume if I have, for example, a temperature of 1.3 TR, or TR is equal to 1.3, and if I had a reduced pressure of 4, which means the pressure is 4 times the critical pressure. P by Pc is 4, which means the P is 4 times the critical pressure. So, what I could do is I can find out this point here, find out the corresponding value of Z on this axis, which is somewhere between 0.7 and 0.6, and I would calculate the V actual as this compressibility factor 0.7 or 0.6 times RT by P. So, I can correct for the volume, which is essentially the correction for the deviation of the volume from the ideal behavior, and then use these values to calculate the other property which I do not know. So, in this fashion I can use, I can deal with real gases and make corrections for the volume which I could not otherwise do using just the ideal gas equation of state. So, this is one level of deviation from ideal gas behavior which we can deal with in this fashion. In addition to this, another way in which we can deal with this is by using what are called tables. So, I can have gas tables for a specific gas. For example, I have air tables, I have nitrogen tables and so on, which would give me properties. So, in those tables I can find out, I can look up the table for a certain pressure and temperature and find out the volume, or I can look at it for a certain volume and pressure, find out the temperature and so on. So, here also I can do the reverse. For example, if I knew the volume, I can find out the pressure and temperature from this chart and so on. So, I can use those values to calculate in problems and get better estimates than if I was to use only the ideal gas equation of state. But what I see is that I do not need to do this if I am either at very low pressures or if I am at very high temperatures compared to the critical point. So, that is something which we will also keep in mind, and we will come back to that in a little while. So, what we see is that in terms of gases, we have looked at different models of gases. So, the first model is a perfect gas where the ideal gas equation holds, but in addition Cp and Cv are constant. So, we also have this in addition to that. So, if I have both these, I call them perfect gases and I can deal with them fairly easily. In these cases, R is known as long as I know what gas it is, because it is just R bar, which is a constant, divided by M, which I would know if I knew what gas it is. Cp and Cv are also known because Cp is gamma R by gamma minus 1. If I knew what gas it is, whether it is monoatomic or diatomic or triatomic, I would know the value of gamma and I can substitute in this. I would also know Cv because Cv is Cp minus R, or it is also R by gamma minus 1. So, I know all of this for the perfect gas. For an ideal gas, I know PV is equal to MRT because that still holds. I still know that R is R bar by M, which is still true. I know that Cp and Cv are still related by Cp minus Cv is equal to R, but I do not necessarily know the Cp and Cv individually because they are both functions of temperature. So, I would need to have the values of Cp and Cv from some table because Cp is a function of temperature, Cv is also a function of temperature. The difference is a constant, but if I need to know the values of each of these, I need them from a table, either the value individually or a functional form, so that I can integrate it in case temperatures are changing. So, this is the second model which we have, which is the more common thing, but at least for the purpose of this course, most of the time what we are doing is assuming perfect gas model, because we do not necessarily know these values of Cp and Cv as functions of temperature. If we are dealing with non-ideal gases, what we saw is we can either use tables or we can use the compressibility chart. And then we have our general model as PV is equal to M, let me put the Z first, the compressibility factor into M into R into T. So, in this case what I can do is I can correct for the specific volumes, or I can say PV is equal to ZRT. I can correct for deviations from the ideal gas behavior by putting in another factor over here. But the next question is, what do we do with vapors? For example, I have water which I am heating and I get water vapor. How do I find out the behavior of those? Can I just use this? We can, but is there a better way to do it than use that? And what do I do if there are mixtures of vapors and liquid? So, the question may be that why do we need to deal with mixtures of vapor and liquid? And we see that mixtures of vapors and liquids are fairly common in real life applications. One of those applications is shown here. This is essentially what is called as a steam turbine. You can see it's a fairly large device. You can see somebody standing here. So, you can quite comfortably fit inside one of these. And these are used for producing electricity. So, you have, for example, a coal plant which would follow what is called as a Rankine cycle, which we will look at in a lot of detail towards the end of this course. The Rankine cycle consists of components, a lot of components. We can sort of look at the four major components which are shown here. We will look at each of these components in detail also during this course. So, it has, for example, a pump. Most of you may have a pump somewhere at home, which is used for pressurizing and lifting up water. So, it takes in low pressure water, gives out high pressure water. We put this into what is called as a boiler. As the name suggests, it boils the water and we are left with high pressure steam. This high pressure steam is something which we expand in a device which is called the turbine, which I just showed you a picture of. And from this turbine, we are left with low pressure steam, low pressure, low temperature steam. So, the steam loses energy and enthalpy while going from this state here to this state over here, and that energy and enthalpy is used to drive a generator which then produces electricity, which we can transport over long distances and use to power on the lights and the fans which are around and any other equipment which we have. And this low pressure, low temperature steam is then sent into a condenser which condenses the steam into water, and this water is at low pressure. It is sent back to the pump and this whole thing goes on in a cycle. We look at the cycle in a lot more detail, but what we see is over here in the boiler, we send in water, we are getting out steam, which means at some point there is liquid water and some point there is water vapor, and in between it would be both. In the turbine, we are sending in steam and we are getting out low pressure steam which could also have some water. In the condenser, we are converting all the steam into liquid, which means there is some amount of vapor and some amount of liquid entering. What is coming out is totally liquid. So, in all of these devices, we have mixtures of water in the liquid form and water in the vapor form, and what we would like to know is how to deal with these kind of mixtures. So, that is essentially what we are going to see.